And this assumes that you've read the first couple of sections of Chapter 9. You'll recall from last lecture what a augmented hidden Markov model looked like. We had states, and these states were sequenced. I should say, though, that this representation scheme, or this presentation scheme, is a bit misleading. So this is an action. This is an action. This is an action. But all these actions have the same domain. They draw from the same set of actions. So these are simply different instances of essentially the same set of actions over time. These are labeled as states, but in fact, they're really steps, because the domain of all these states are the same. You can draw from the same state space. So this is a state at step 1, state at step 2, state at step 3, etc. But they're all potentially from the same state space. So the domains are the same in all cases. So I've called them states here. In the illustration from the book from which this is drawn, these are called locations, but these are the same domains. And then observations can be made at each state along this Markov chain. And all of these observations have the same domain. And so this is a belief network, just like essentially any other belief network, except there's a temporal ordering here, something that is interpreted typically as a temporal ordering. And at each of these nodes, we're going to have probability tables. So, oh boy, I've got to go back and I've got to revise these slides before I post them. This probability table is going to be the probability of observations given states. So I've written these here as unconditional probabilities, but I will revise that. This is actually a probability of a particular observation given a particular state. So these are actually conditional probabilities here. These are unconditional probabilities. These are actions, possible actions that an agent can take that correspond to possible actions. And these are unconditional probabilities. The probability tables of a state node are going to be the probability of a state at some step, some time t, in this case 2, given the state of the previous step and the action that's taken. So each of these steps is dependent on two items, two sources of information, two sources of influence. So in the illustrations in the book, a state is often equated with a location. They're talking about robotic applications. But a state can be a joint outcome space. So a state can correspond to something that, something like the robot coffee delivery system and mail delivery system. So each of these states here, the domains there, can be drawn from a population or a domain that looks like this. The robot is in the coffee shop, the robot has coffee, Sam wants coffee, and then these are about the mail system. And so in this case, we might represent a conditional probability at one of these locations. The conditional probability of this state, given a prior state and an action, pick up coffee, in this case is very high. And we might expect this to be high because the pick up coffee preconditions are that the robot is in the coffee shop and the robot is not holding coffee. And this is also consistent with the mission of the robot, which is to deliver mail and deliver coffee to office personnel. So we would expect this to be a high probability. But we can also have instances like this. The probability that the robot has coffee is in the lab, Sam wants coffee, given that the prior state is the robot doesn't have coffee and the robot is in the lab, and the action is pick up coffee, the probability of that transition is going to be 0 because the preconditions for pick up coffee aren't satisfied in this case. Coffee can only be obtained from the coffee shop, it cannot be obtained from the lab. So in this case, it's 0 probability. So we can interpret, these can be actions that have no effect. So the result here, if you were to think about this, the probability that the robot is in the lab, the robot does not have coffee, Sam wants coffee, given the same state here. So given this state, the probability that the robot will remain in the same state given pick up coffee is going to be 1. Because that transition is not going to happen and no change is going to be made. You can do, again, filtering with hidden Markov models. And the format for filtering is we have got a information about prior observations and actions taken. And what we want to do is we want to take the best guess. We want to compute, I shouldn't say take the best guess, we want to compute the probability that at time t, given all prior observations and all prior actions, what is the probability that the robot will be in, or the current state will be a particular value. And remember, these states can take on multiple values. So big S1 is a probability distribution over states. Little s sub k is a particular value for states. And so if we want to compute this probability, we could just solve that just like we would solve any problem for a belief network, which covered early last week, Tuesday, in the pre-recorded lecture. We would take a conditional probability like that. We would expand it into a joint probability over a joint probability of the conditioning information. In this particular case, we want to solve for this, the probability of this given this and this. But to do that, we've got to do what I called filling the gap in the prior lecture. We've got to sum over all possible values for S sub 0. So we're summing over S sub prime for all possible values. And that's going to give us this, but we're going to take this and we're going to transform it into a conditional probability, which we can rewrite this way. And then after simplifying it, I didn't simplify it all the way, but I simply wanted to show that at some point you get an expression in which you can factor out the probability of a given action. And that occurs in both the numerator and denominator, and those are going to cancel out. So that this final expression, when you've actually fixed the value of the action, this does not affect the probability computation. It's as though when you fix the value of that action, the probability for that value is probability 1. And so that is the intuitive interpretation there. But it just stems from canceling those two out of both the denominator and numerator. So this is important because we're going to get to talk a bit about planning. And when I talked about probability tables here for actions, this might be something that's important for an observer of a robot who's interacting in the world. The observer is watching the robot act, and with various probabilities, the robot, or whatever agent this is performing different actions. But in a planning context, the agent is actually fixing certain values and then making decisions based on that fixing of values, those constant values. So in this case, an agent might be picking particular actions out of here, then conditioning, looking for conditional probabilities based on that fixed value and making judgments on it. So we fix this, and this is going to lead to, for a particular action under a particular observation of prior states, this state, S sub k, might have one probability, and other states might have different probabilities, because these actions typically are non-deterministic. They may not be deterministic, and the effects may not be guaranteed like they were in chapter 6 when we talked about planning under certainty. This augmented hidden Markov model defines a search space. It specifies a search space. And there's going to be a lot of possible initial states, because remember, the domain of this is the set of all possible states. It's the same as the domain for this, the same for the domain of this. But for a particular state taken from the domain there, for every action, remember the domains of all the action steps are also the same. We can simulate each action, and this is going to give us a child state or neighbor state. So if I apply action P to whatever this state A is, I'm going to get one possible state. We're going to qualify this in a minute, but we're going to get a new state B. And actually, because of the uncertainty associated with actions, we may get any of a number of new states after performing that action. If we apply action Q, we may get any of a number of new states for the next state after applying that action. If we apply the action here, another action here, let's say it's action R, we'll get yet another state. So each arc here is intended to represent the selection of an action and application of an action from one state to the next. And so, and then there's going to be probabilities associated with these. This state, the probability that you'll get state C after applying an action, what we're really computing here is the joint probability of C, action, and prior state. And this joint probability is an indication of how likely the this outcome is given that action applied to that state. Some of these, again, because of the fixing of particular values, action and initial state are going to simply be 1. The probability that the initial state is A, given what we've said, is going to be 1. And the probability of this action being taken is going to be 1. The other, what follows though, this is not necessarily going to be 1. It is going to be based on the probability of C given A and that action. And again, that is stored in the probability tables for each of these states, the probability of each state given a particular action, particular prior state, are in those probability tables. Now, if we are searching for goals in this case, let's say that C and, or that's E and F are goals. This process of doing a search expanding the search state until we find a goal, we could do this in a depth-bounded way, or we could use breadth first search or some other procedure. But we're going to expand the search space. And when we get to goals, we can compute the probability of this goal state, the action taken, and the prior context. So we can actually compute the probability, the likelihood of each goal in this search space given the probabilities that we stored. And that would be something that you might use to make a decision as to where you should go in this case. The agent is doing this look ahead, this search, in order to figure out, should I take that action, or should I take that action, or should I take some other action? And certainly when we talked about search in chapter 3, cost was the primary consideration, but the likelihood of certain outcomes is another potential consideration. And this allows us to do it. So the important thing to remember, this defines a search space, and we can expand based on the actions. It's typically the case, I shouldn't say it's typically the case, but it's often the case that we're not told that there are some states which are goals and some states which are not goals. We're told that some states are better than other states. And I'm not going to review the reading on this because I think it's pretty clear on utilities and the axioms of rationality that you read for this. But it's more likely the case that we can assign utilities to each state. And some states, again, are going to have higher utility values than other states. So there is a ordering. Things can be weakly ordered or strongly ordered. And the goal of the agent typically is to get to states with higher utilities in this more general setting, not simply goal states, but higher utility states. I think who's in the yellow? Yeah, what, Ethan?
Yeah.
So I think Ethan asked about this 2 months ago. Didn't you ask me, isn't there a better way? Aren't there contexts in which we don't have goals? I think I remember you asking that, but this is more likely the situation that we are given utilities, and the agent is going to reason from utilities. Again, we can expand this, and we're going to represent this in a slightly more sophisticated way, given what's going on. And if you remember the initial lecture on probabilities, when we talked about probabilistic or expected minimax, this harkens back to that representation a bit. But we've got the same kind of search space here, and we're assuming this representation for the hidden Markov model. We have a particular start state. So it's a state that's been drawn from this population, and it's certain. And we can apply operators, actions, from the domains of these actions. Here I'm just illustrating two in each of these cases. So we can apply operator 1 to that state. We can apply operator 2 to this state. And unlike the earlier figure that only showed one descendant here, in fact, there might be many descendants here, because operator 1 in a context in which we have uncertainty might produce multiple effects. Some of the effects of the operator, assume a strips representation, some of the effects of the operator will in fact might be true after the application of the operator, but in most cases, some of these effects are going to be true only some of the time based on a probability distribution that's been specified for them. So it may be that the robot does in fact pick up the coffee, but it spills or it is dropped. And so after the pickup coffee operator, it is not a sure bet any longer in an uncertain domain that the robot is holding the coffee. The robot, if the robot is sure-handed, is only holding the coffee with 95% or 0.95 probability. And 0.05 of the time, the cup has been dropped and the robot is not holding the coffee after application of the pickup operator. And so we might have multiple possible outcomes. Well, we're only going to have one outcome after applying this operator, but we don't know what it's going to be with certainty typically. And these probability tables are going to specify for us what the relative likelihoods are. So remember, in the probability table for this is stored the probability of some state here, call it B, given a particular action and given action here and a given prior state. So we might end up in B with some probability, we might end up with C and C with some probability, and we can continue this search. This may be a dead end. Some may be a dead end, and that this may have a particular utility assigned to it. But then we can repeat this process, and at state B, apply operator 3, and we come down here, and there's a couple possible outcomes with that result from applying operator 3 to state B. One outcome gives us state F, one outcome gives us state G. Operator 4, also uncertainty associated with that. And so for each operator in this context, we're going to have one of some number of outcomes, and each of those outcomes is going to be associated with a probability of it being that outcome. And again, each of these states, state F has a utility associated with it, state G has a utility associated with it. Each of these states is going to have some kind of utility. We can compute, so if we're considering this node and we're asking ourselves, okay, what is the expected utility from this node? This node has two outcomes as illustrated here. One has a utility for F, the other outcome is G, that has a different utility. Outcome F is going to happen with a certain probability. Outcome G is going to happen with a certain probability. And so the expected utility of this state is emanating from that node is going to be the probability of this state, given where we are in this tree, times the utility of that state. And we're going to add that to the probability of this state times the utility of this state. It's like a weighted average. And so this is an expected utility that is associated here. If we get here, can't be sure about what the outcome here is, but on average, we can assign a value as to what we expect. At this node, we also can compute the expected utility of this node as well. Simply going to be the probability of H times the utility of H plus the probability of I times the utility of I. And again, that's going to give us a weighted average. At this node, we can think of this as taking the max. Because we're in a context in which the agent has control, the agent is exercising control in this planning context. The agent presumably is going to go down the maximum value. This might remind you a little bit of minimax search. There's an adversary. And so in minimax search, you're taking the max of mins. The opponent that you're playing in a game is going to try and foil you and try and take steps which minimize your score. You're going to try and maximize your score. In a situation in which you're just dealing with a single agent, that single agent, presumably, if it's rational and it follows the axioms of rationality, it will choose to always maximize its score, maximize its expected utility. The book talks about humans not always following these rules using expected values. If you are offered $400,000 firm, or if you are offered a lottery, flip a coin, and if it comes up heads, you get $1 million. If it comes up tails, you get 0. Many people are not going to go for the lottery. They'll go for the sure bet, even though the expected value in the lottery is higher. So humans don't necessarily follow this rule because they tend to be one-shot gamblers, I suppose. If you're a professional gambler, you might go for that all the time, but then you're part of a repeated trial. Now we can compute the expected utility of this node. It's going to be the probability times the utility of this node plus the probability of this node times the expected utility of that node, which again is just given the max. And so what we're doing is we're simply computing these utilities bottom up. And for the final exam, I would expect you to be able to compute these utilities from the bottom up. Again, for exam 2, this is material that I won't ask because it's strictly speaking from chapter 9. We do the same thing for this subtree, and up here we are going to be selecting the max between the expected utility here and the expected utility here. If the expected utility here is greater than the expected utility here, we're going to choose the rational agent would choose to make a move down this branch. Yes?
Would it be possible for a state to show up twice on this graph? So like for instance, if state C is possible through operator 1 and 2.
Yes. Yeah, this is really a DAG. You can have reentrancies, you can have repeated states here. And we might go through that in, there's similar kinds of rules of pruning as there are for search of graphs in a deterministic situation. But yeah, you can have reentrancies. That will complicate this somewhat. Oops.